Today we're going to be talking about some basic principles of gases, including Dalton's law, and how that relates to human respiratory physiology. And then, as we near the end of this session, we're going to talk about how that relates to air travel and the pressurization of airplanes. Let's start with Dalton's law, though. And what that tells us is that the barometric or atmospheric pressure anywhere in Earth's atmosphere, is going to be equal to the partial pressures that individual gases present exert. And so what that means is that we're going to have the partial pressure of nitrogen, which is the most prevalent gas in Earth's atmosphere, plus the partial pressure of oxygen, and then the partial pressure of a few other gases. And it turns out that the other ones I'm just abbreviating as X, but those include argon, carbon dioxide, neon, helium, etc., but that those exert very, very low partial pressure and really don't contribute very much to the atmospheric pressure in Earth's atmosphere. The vast majority of that is contributed by nitrogen and oxygen. This is an important law for many reasons. However, let's look at what it means by using some numbers as examples. So what's the typical atmospheric pressure in millimeters of mercury at sea level? Yep, that's right, it's 760 millimeters of mercury. And it turns out that nitrogen makes up roughly 78% of the atmospheric gases by volume. And so that works out to be approximately 590 millimeters of mercury that are devoted to nitrogen. And then oxygen makes up approximately 21% by volume, and so therefore works out to approximately 160 millimeters of mercury. And again, the other gases are much lower. You can see that we're almost at 760 just by those two gases. And so again, the same thing is true that if we take the total fractional concentration of gases, well, all the gases that are present in Earth's atmosphere are going to equal 100% of those gases, and therefore the fractional concentration of nitrogen and the fractional concentration of oxygen are going to contribute, and we know that for oxygen that's 21%, and for nitrogen that's approximately 78%. And all the other gases that we're talking about are going to contribute approximately 1% to the total concentration of gases. And so that's Dalton's law, and this is just important to keep in mind because it is very important relative to the different fractional concentrations of gases and how we think about different gases contributing to the overall barometric pressure at a given altitude. So how does this relate to human physiology? Well, there is an important formula called the alveolar gas equation, and we're not going to delve into the full details of that. Instead, what we're going to think about is the partial pressure of inspired oxygen. So the partial pressure of inspired, the I stands for inspired, and the O2 stands for oxygen. This is basically how much oxygen is out there in the air that we're breathing. So the fractional concentration of it. So the fractional concentration of inspired oxygen times whatever barometric pressure or atmospheric pressure we happen to be at. And so again, that'll vary based on your altitude. So again, let's use sea level as our example. And we've kind of already done this in our last example here, but the atmospheric pressure is 760 millimeters of mercury at sea level. And we're going to multiply that by 0.21 or 21%, which is about in ambient air, the air that we breathe, the percentage of oxygen. And so that value we already know is going to come out to 160 millimeters of mercury. And so the partial pressure of inspired oxygen in the air we breathe is 160 millimeters of mercury. If I were going to show you the full alveolar gas equation, we would see that the maximum amount of oxygen partial pressure that we can have in the alveoli of the lungs is roughly 100 millimeters of mercury under normal conditions. And that can vary slightly from there. It would be unlikely or almost impossible that it would ever get to 160 millimeters of mercury. So this is what we start with. The air that we breathe has a partial pressure of oxygen of 160 millimeters of mercury. And we see that there are two things that contribute to that. One is the atmospheric pressure, and the other is the fractional concentration of oxygen in the air that we're breathing. So how does this relate to air travel? Well, if you'll think about this for a minute, when we travel in an airplane, we're going to be typically a commercial airplane, a passenger airplane. We're going to be traveling at altitudes up to 40,000 feet above sea level. And so if the airplane was not pressurized and we were just at 40,000 feet, then the barometric pressure would be incredibly low. And if that were to happen, then with our fractional concentration of oxygen staying the same, so again, we're just going to use the same equation here. If this atmospheric pressure went down to, let's say, 300 millimeters of mercury, and the fractional concentration went down to still 0.21, because again, it doesn't matter at what altitude we are. As long as we are on Earth, the fractional concentration of oxygen is going to be 21%. So if we do this calculation, we're going to see that we're going to be at approximately 60 millimeters of mercury. And that's the best we can do in terms of the amount of oxygen getting to the lungs. And it turns out this partial pressure of 60 would be very detrimental to human health. That would be a very, very low oxygen value to start with, and it would only be lower by the time that reached the alveoli, the area of the lung where gas is exchanged. So we can't do that, and so instead we have to pressurize the cabins of airplanes. And so we pressurize those cabins such that when you're at a cruising altitude of 40,000 feet, most airlines are able to pressurize the cabin not to sea level, not to 760 millimeters of mercury, but instead are able to pressurize to approximately 4,000 to 6,000 feet above sea level. And that works out to be roughly an atmospheric pressure at 6,000 feet of 600 millimeters of mercury. Okay, so if we again use our equation, so again the partial pressure of inspired oxygen equals our fractional concentration of inspired oxygen times the atmospheric pressure. And we say that the atmospheric pressure here is 600. And we take our fractional concentration of 0.21. What we're going to see is that our maximum partial pressure of inspired oxygen is now approximately 120 millimeters of mercury. Okay, and that's a reasonable number to start with. That's going to allow most people to have a partial pressure of oxygen in their alveolus in the lungs of roughly 80 or 90 millimeters of mercury, and that's reasonable to sustain your oxygen values in the blood and not make you feel short of breath. However, and this is the message that most of you have probably heard before if you've been on an airplane, if there is a sudden change in cabin pressure, oxygen masks will deploy, and you should put one on yourself before you put one on your screaming child. And so the concept behind this is simple. The idea is that if there is a breach in the hull and the airline cannot be pressurized to 6,000 feet above sea level and instead is at 40,000 feet above sea level, that partial pressure in the atmosphere is going to drop, and let's say it drops to 300 millimeters of mercury. Well, we know that the only way, based on this formula, that we can do anything to improve the amount of partial pressure going to our lungs is by increasing the fractional concentration of oxygen. And the only way to do that, again, because the atmosphere at ambient conditions is 21% oxygen, is to increase that amount of oxygen through the supplementation, through the mask. The oxygen mask is delivering a higher fractional concentration of oxygen. Let's just say, for the sake of argument, that we're able to get that up to 50%. 50% of the air we're breathing is oxygen. That means that the partial pressure of inspired oxygen is going to be able to go up, in this case, to 150 millimeters of mercury. And you can see that that gets us back almost to our normal value of 160 millimeters of mercury. And so this hopefully explains to you why, when there is a sudden change in cabin pressure, oxygen masks are deployed. It's essentially allowing us to accommodate for the drop in atmospheric pressure by increasing the fractional concentration of oxygen that we're breathing, and thus allowing us to maintain our oxygenation and not feel short of breath. So I hope that was helpful in explaining this. I look forward to your questions.